In this video, we'll describe how to interpret output from a SaTScan analysis that prospectively detects outbreaks of a community-acquired communicable disease. To follow along, download the corresponding sample analysis files from the SaTScan website at satscan.org. At the end of this video, you should be able to interpret SaTScan analysis results by reviewing automatically produced output files, including the text-based results file, maps, a line list of cluster events, and temporal graphs. Presented here are the results of an analysis that uses the network input file to scan for clusters along a network, rather than using the default circular scanning window. To reproduce these results, make sure to point to the sample network file on the Network tab of the Advanced Input Features window in the SaTScan user interface. To avoid overriding results from previous analyses that didn't use the network input file, rename the output file on the Output tab. And to ensure that events are correctly flagged as newly identified, make sure the cache file hasn't been overwritten in previous analyses. More details about the network input file and cache file are provided in other video tutorials and in the how-to document provided with the sample analyses files. When an analysis is finished running in the SaTScan user interface, a results window appears with the results of the analysis. These results are also saved as a text-based file in the output folder and contain information about the analysis, the input data, and the clusters detected. The first section of the file contains the analysis information and shows that we ran a prospective spacetime analysis scanning for clusters with high rates using the spacetime permutation model. The next section summarizes the input data and shows that our study period is 1 year long, ending January 20th, 2026, and includes 2,284 census tracts and 2,537 cases. The file also contains information about detected clusters, including spatial information for each cluster. We're using data at the census tract level, and the cluster census tracts are listed in order of centrality. Here, for example, cluster 1 includes 92 census tracts. Typically, all census tract IDs are listed, but they're abbreviated here for simplicity. The coordinates of the cluster centroid are also displayed. You must use latitude and longitude coordinates to be able to request map output files, but you can also use Cartesian XY coordinates if you want. The next two lines display the span of the cluster, which is the longest distance between any two census tract centroids in the cluster, and the temporal extent of the cluster. For prospective analyses like this one, the time frame will always encompass the last day of the study period. Additional cluster information includes the number of cases in the cluster versus the expected number of cases and the observed over expected value. Cluster 1 contains 30 cases, while the number of expected cases is 6.66, so the observed over expected value is 4.5. The expected number of cases is a function of the proportion of cases in the cluster area during the baseline period and the citywide volume during the cluster period. Clusters are listed in order of decreasing test statistic. For prospective analyses, each cluster has a recurrence interval, which is an alternative to the p-value. We use recurrence intervals instead of p-values because applying the typical threshold of p less than 0.05 would not adequately control type 1 error in prospective analyses, and it would, on average, generate a false signal every 20 days. The greater the recurrence interval, the less likely the cluster is due to chance. We consider a recurrence interval greater than or equal to 100 years as a very strong cluster, between 5 years and 100 years as a strong cluster, between 365 days and 5 years as a moderate cluster, and between 100 and 365 days as a weak cluster. By this rule of thumb, cluster 1 is considered very strong and should be prioritized for further investigation. Cluster 2 is a moderate cluster. Its recurrence interval is one factor to help decide whether further investigation is warranted. Cluster 3 is another moderate cluster, and cluster 4 is considered weak with a recurrence interval less than a year. While its recurrence interval is relatively low, other factors might suggest that it should still be investigated. For example, cluster 4 is geographically small, including only 5 census tracts, and its observed over expected value is very high. 7 cases were observed when only 0.44 were expected. Other SaTScan output might provide more clues about whether this is a concerning cluster. You can request SaTScan produce other output files that aren't generated by default. For example, another tool for cluster review is a line list of cluster events, which you can request that SaTScan produce when importing your case input file. See the Advanced Input and Output Features video to learn more about how to request this and other optional output files. This is a subset of the line list output for the sample analysis. It has a row for each individual ID in each cluster. And by specifying a cache file in the case file import wizard, you can request that SaTScan distinguish which events are newly added to a cluster since the last time the analysis was run. If you don't specify a cache file, every event will be flagged as new. The line list can also include descriptive longitude and latitude coordinates for each event. These allow you to display individual case locations on a map. These aren't the coordinates used in the analysis, which are the coordinates of the census tract centroids listed in the coordinates file. The line list also contains any other characteristics included in the case file and specified in the case file import wizard. This is a subset of the line list for events in cluster 2, where we see that most events are labeled as secondary in the hierarchy column. Secondary events are those that also appear in a stronger overlapping cluster, in this case cluster 1. Event ID 2532 toward the bottom is labeled as primary, meaning that it appears in cluster 2 but not cluster 1. Considering again whether cluster 4 warrants further investigation, we can look at the line list of cluster events for cluster 4 and notice that most are among children, which could indicate an outbreak in a group setting for this age group, such as a school. While demographic characteristics like this can help investigators find clusters in settings like schools, this analysis is searching for community-acquired outbreaks using patients' home addresses. We recommend using other methods for detecting facility or building level clusters. Map output files can also help with cluster interpretation. We typically request HTML and KML output files for visualizing clusters in Google Maps and Google Earth. This is an example of an HTML map output file. You can interact with the map by clicking on each cluster, displaying the cluster summary information, including its time frame, the number of observed and expected cases, and the observed over expected value, the test statistic, and the recurrence interval, which is very high for cluster 1, meaning it's very unlikely to have occurred by chance. You can also roll over clusters to see their spatial extent and whether they overlap with other clusters. And you can control which clusters appear on the map, either by defining a recurrence interval cutoff using this slider, or by selecting clusters by their index number. So now if we want, we can focus again on cluster 4 and zoom in. If you specified individual IDs and their coordinates in the case file import wizard, you can select Use dots to display. By default, dots represent cluster locations, but you can also choose to display individuals. Individuals in the selected clusters are displayed as red and outside as white. You can click on each icon to see the individual characteristics that were included in the case input file. Here we see that this event occurred on January 18th. It's part of cluster 4, and the individual is a female in the 0 to 17-year age group. The disease code and disease status variables were also selected to be included in the cluster line list and are displayed here as well. You can play a movie to display individuals on the map in order of their event date, and you can control the time frame and the speed of the movie. There's also an option to exclude individuals from the map For example, you can choose to exclude those outside the cluster and temporal window. There are a few additional options to control the appearance of the icons, like their size, color, and shape. For example, you can choose to distinguish by color which cases are newly added to the cluster since the last time the analysis was run, where bright red now indicates that individuals are newly added. You can also use shapes to distinguish by other characteristics. For example, you can unclick all circles and click on all of the age group categories to categorize by shape. And you can also increase the size of the icons to see them better. Here, all except 2 cases in cluster 4 are circles, meaning they're in the 0 to 17-year age group. Are circles, meaning they're in the 0 to 17-year age group. The KML output file, which you can view in Google Earth, has similar functionality as the HTML map. You can overlay cases and visualize them over time by moving this time slider. And you can group individuals by different descriptive variables, such as by age group. Here I'm clicking on the legend to show that different shapes indicate different age groups. You can also click on icons to display event characteristics like you can in the HTML map. But one advantage of visualizing clusters in Google Earth is that you can overlay multiple files. So you can add layers with contextual factors. For example, here I'm overlaying school locations. These locations aren't included in SaTScan files, but they may be helpful to display for cluster investigations. Another new SaTScan feature is the ability to visualize risk estimates for each location. Checking this box will request SaTScan create an output file containing the observed over expected ratio and the relative risk for each location, either as an ASCII or DBase file. And it'll allow you to visualize the observed over expected values for each census tract in the Google Map output file. Now you can choose to use dots to display the observed divided by expected, or the ODE values for each census tract. Red dots mean higher ODE values, and you can see there are more red dots within cluster areas as you would expect. You can click on each dot to see the observed and expected number of cases and the observed divided by expected value for each census tract. For example, in this census tract in cluster 4, there were 2 cases observed when only 0.35 were expected for an ODE value of 5.77. You can use this feature to explore whether other areas of the city, even if not part of a detected cluster, also have elevated ODE values. It could be that residents of those areas are somehow connected to people residing in cluster census tracts, for example, through shared cultural characteristics. We also recommend outputting temporal graphs for review, as these provide additional information that can be helpful for cluster investigation. You can request that temporal graphs be produced on the Temporal Output tab of the Advanced Output Features window. We typically restrict the temporal graphs to be output for clusters with a recurrence interval greater than or equal to a threshold, such as 100 days, to reduce the volume of output. While maps help visualize clusters in space, temporal graphs display clusters over time. For prospective spacetime permutation analysis, temporal graphs contain 4 time series. The observed cases in the cluster area are displayed as dark blue bars outside the cluster temporal period and red inside the cluster temporal period. The expected number of cases is the dark green line, which is hard to see in this graph. It's down at the bottom. The observed divided by expected values are represented by an orange line, and observed cases outside the cluster area are represented by light blue bars. You can hover over a date to display all of these values on that date. For example, on this date, there were 3 observed cases in the cluster area when only 0.61 were expected, resulting in an observed over-expected value of 4.56, and there were 13 cases observed outside the cluster geographic area. You can also zoom in on the graph to see a smaller time period more clearly. And you can reset the zoom. Use the button in the upper left to select which cluster temporal graphs to display. Looking again at cluster 4, we can deselect the first 3 time series to see that cases outside the cluster area in light blue appear slightly elevated during the cluster period indicated in the gray band. But selecting only the first time series, we see that cases inside the cluster area are elevated during the cluster period, displayed in red, compared to its own baseline. In the chart options section below is a 2x2 table that shows that during the cluster period, 9.3% of cases citywide were inside the cluster area, which is higher than during the baseline period when only 0.3% of cases citywide were inside the cluster area. Considering together all of the output files we reviewed, it's clear that despite being classified as a weak cluster according to its recurrence interval, Cluster 4 is localized in space and time, has cases that are mostly among a specific age group with new cases added since the analysis was last run, and has a higher percent of cases inside the geographical cluster area than during the baseline period. And this all suggests a potentially acute and ongoing outbreak that should be prioritized for further investigation.